So welcome everyone. This is the final general meeting of 2020-2021 board. And we will have an election after this. So please stay in up until the end. And with that, it is my pleasure to introduce Dr. Hazem Jadallah. He received his bachelor's degree in civil engineering from Cleveland State University. He received his master's in business administration from Case Western Reserve University. He has recently defended his PhD dissertation from Louisiana State University. Dr. Jadallah has experience as engineering product specialist and global sustainable construction consultant for construction chemical divisions of BASF, and he continues to be employed after the reorganization as master builders. He is a member of ACI Committee 440, Fiber Reinforced Polymer Reinforcement. Please join me in welcoming Mr. Jadallah. The floor is yours.
Thank you for having me. As was mentioned, my name is Hazem Jadallah. I'm going to be discussing strengthening concrete structures with FRP systems. And I guess without further delay, let's dive into the presentation. So before we get started, I'd like to just go over what the learning objectives are for the presentation and what I'd like to achieve. So I'd like to begin by establishing an understanding of what FRP materials are and how they behave, followed by learning how to evaluate whether FRP systems are appropriate for a particular strengthening application. And finally, we're going to get, without going into too much detail, but understanding the means and methods and requirements for actually installing these systems. A little bit of field installation, application type of information at the end. So fiber reinforced polymers are, as this graphic shows, a string of fibers going in a singular direction. And there are bidirectional fabrics, but just to keep it simple, here we have a unidirectional weave or fabric encapsulated by a polymer or resin. So the graphic here shows several individual bars. Each one of those bars is a fiber of material. In this case, carbon is what we're looking at, or what's kind of described in the graphic. And just so you have an appreciation of what these fibers really look like, or just how small they actually are, the line here, the black rod, is a carbon fiber, and the rod going perpendicular against that rod is a human hair. So you see in 1 square inch of this material, we have several million fibers going in a single direction to carry tensile loads. And while I guess I've brought it up, these fibers are primarily or exclusively, really, I should say, designed to take tensile loads. They really haven't been thoroughly tested in compression. It's actually kind of dangerous to test them in compression, because if you try to compress the fibers, there could be a shattering effect. The fibers can become airborne and respirable at that point. So exclusively in tension or tensile applications. FRP materials are relatively new in the construction industry. And when I say relatively new, they've been used regularly in construction for, the past 35 to 40 years. In construction kind of terms, that is, relatively new in the grand scheme of things. They have been used in several other industries for quite some time, however. And the reason is they have very attractive material characteristics. They have very high strength, about 10 times the strength of standard 60 KSI steel. They're extremely lightweight, so about 1/10 the weight of steel, and they're non-corrosive, which is extremely attractive in our industry because the leading cause of concrete repair is due to corrosion from the reinforcing steel in the concrete. So if we can have a material that is non-corrosive by nature, then it's extremely attractive in the industry. It's been used, as I mentioned, in other industries because of the material characteristics. So for example, in aerospace, the picture on the bottom left here is the Boeing 787 Dreamliner that is made almost completely of carbon fiber. And again, due to the high strength, lightweight characteristics of the material. Shipbuilding, automotive, have also used carbon fibers, and then finally sporting goods. So if you're familiar with fishing rods, or if you are familiar with golfing, for example, usually the more high-end golf clubs are graphite golf clubs. Graphite is just a brand name for carbon. There are three main types of fibers that are currently present in literature in ACI 440, and two of which are used, semi-regularly. So carbon fiber is used, I would say, just a rough kind of estimate, 80 to 90% of the time. That's usually the go-to. Glass fiber is used in other applications, and I'll get into why you would use glass over carbon. Aramid fiber is almost never used. I mention it because it's still in the literature in ACI 440. Aramid is probably more recognizable under its, the popular brand name Kevlar, and it does have strong resistance for blast reinforcement. However, the cost of the material itself was really way too high to be used regularly in construction. So people have just adopted carbon in its place, and it's been really phased out in actual practice. But again, I mention it because it's currently in the literature. If you look at this stress strain graph of the three materials I mentioned, you can see that these materials are really the definition of a brittle material. They will continue to take load until they can no longer take load, and then they fail. And we can also see just how strong these materials are. So carbon is the strongest of the materials, has the highest strength, followed by aramid, followed by glass. And as you can see, when we compare it to steel, as I mentioned, it's about 10 times stronger than 60 KSI steel. Carbon has a strength of about 550 KSI. And whereas steel will yield over time after a certain point, carbon will not. And I'll get into kind of how we design with the relationship of carbon and reinforcing steel in mind throughout the presentation. So getting into FRP in construction. So the externally bonded reinforcement. So if you have an existing structure and you want to install FRP after the fact, there's really two main reasons why you would go about doing this. The first is strengthening. So you want to upgrade a load on a structure. So for example, let's say we have a 3 or 4 story concrete structure and we want to add another floor. Everything underneath has to be strengthened. Seismic retrofits, if a building wasn't or a structure wasn't initially designed for seismic, but codes have been updated, and blast hardening, I have an example of that later on in the presentation. And then structural rehabilitation. So if the structure has been damaged for some reason. So restoring corroded rebar, impact damage. So if there was an actual impact into the structure and the tensile reinforcement was misaligned, you can use FRP, and then reinforcing slab cutouts. And again, I have an example of that coming in later in the presentation. Going into the types of FRP systems, the first I'll discuss is a fabric system. So you have a fabric that comes in a roll and you apply it to the concrete substrate with an epoxy saturation that allows it to bond to the concrete. So you would apply an epoxy to the substrate, then apply the fabric, and then another layer of epoxy so that the fabric is fully bonded and can take the load. Now, I like to draw the comparison between FRP installations and more conventional methods. So here you see a parking garage where they are bonding FRP to the column. Now, if they wanted to increase the capacity of the column using more conventional means, they would have to enlarge the column, which requires pouring concrete around it, which takes up more space and adds dead load to the structure, whereas FRP essentially has no dead load. And if you think of, again, a parking garage where it has an owner and they're trying to run a business, if you enlarge columns and you enlarge all the columns, that's less spaces and essentially less money that the owner can make. So if you can take something with a very small cross section and essentially no impact to the overall structure, it's very attractive to the owner. The other thing that has typically been done before FRP was widely utilized is bonding steel around certain structural elements like columns or beams. And again, that greatly increases the dead load of the structure, and that needs to be taken into consideration. The next type of system is a surface-mounted laminate. So these are basically pre-cured strips of the fabric. So instead of having to take a fabric and apply it using, having to deal with the contouring of different shapes, and it's a little bit more difficult to deal with if you're trying to apply this material on a flat substrate. If you know your substrate is already flat, it's easier to bond a laminate, which again is a pre-cured strip, using epoxy to the concrete substrate. This is ideal, obviously, for flexural applications. Here you see mid-span the installation of FRP laminates. And then the last system I'll talk about are near surface mounted bars or NSM bars, which are ideal for traffic type applications. Here, this is actually the Cleveland parking garage where I'm currently sitting. The Cleveland Airport parking garage, sorry, where they needed to reinforce this area of the slab because the beams underneath were actually too deep and larger sized cars couldn't get through. So they needed to decrease the depth of the beam, reinforce over top. Now these are installed by cutting a 1/2 inch by 1/2 inch groove shown in the graphic, placing the bar and backfilling with an epoxy. Now the epoxy typically cures within 3 to 4 days, and after that you can open it up to traffic. Again, if you were to try to use more conventional methods, you would have to remove the first layer of concrete, put a steel plate underneath, and pour additional concrete over top. Again, this is very time consuming, and really the main draw of why someone would choose FRP is really not the material cost, because the material cost is greater than the cost of steel. It is really the labor and time savings. The turnaround is much, much quicker. So the benefits of external FRP systems, as I mentioned, really with the column example, is they're flexible and can really contour to any substrate. They're easily installed overhead, and they're versatile. So here, when you have an irregular geometry, it's easy to have FRP contour to that shape to increase the load of a beam. It's very easy to layer systems or have layers of FRP go over top one another. So you can reinforce in multiple directions. So here you have the underside of the bridge where we're reinforcing in multiple directions, and it's easy to do this because the thickness of a fully cured system of FRP per layer is about 1/16 of an inch, or just to kind of give a mental, image, about the thickness of a credit card. So if you can easily layer 2 credit cards over top of each other, and it really doesn't add any extra shape or take any extra area in terms of the structure. And it's easy to conceal. So if you can take a simple coating and coat over top of an FRP system, and this really has 2 benefits. The first is the system is not, or the epoxy is not UV stable. So over time, if it's exposed to sun, the system will begin to chalk, which could potentially compromise the system. So it's good to coat it with a UV stable coating so that doesn't occur. And then just simply from aesthetic purposes. So here you have, a bridge underpass. Most people don't feel comfortable about, under driving something, or about driving under something like looks like this, because they feel like their bridge is essentially scotch taped together. So just from a peace of mind standpoint, people would much rather look at this. They can be applied in areas with limited access. So here we have a hospital application where the floor above this slab was initially designed to be a patient wing, and they repurposed it for more heavy equipment. So they needed to strengthen underneath. So they were able to go in, remove a few ceiling tiles, and install the system without really shutting down parts of the hospital. Again, if they were to try to do this using more conventional methods, they would have to go in, likely close down large sections of the hospital, bond steel to the underside of the beams and slab to reinforce to meet the design requirements of the floor above. The ACI Guidelines and Standards are shown here. So ACI 562 is kind of a more comprehensive overall concrete repair code. And I have it here because they do reference FRP in the document, but again, it's not really the main idea of the code. Whereas ACI 440 is a code for actually designing FRP systems. So the 2R document gives guidelines on how to design the systems, and then the 0.8 document discusses the material specifications. So how do we go about selecting which system should be used in a specific application? So we have a few considerations that need to be made before we go ahead and select a system. So environmental considerations, loading considerations, and then durability considerations, and I'll get into more detail. And then there are strengthening limits in terms of the bond between the material itself and the substrate through the epoxy, and then fire endurance. So if you look at the graph that shows the exposure to the carbon system and the glass system over time, we see that the strength retention for glass is significantly less than that of carbon. Over time, it becomes much weaker. And it might be better illustrated by this table here, where you see the overall design strength is limited by an environmental reduction factor. And you can see what these reduction factors are for each material given the exposure. So in the best case scenario, you have carbon, and then in an interior exposure, you assume 95% of the design strength from day one, which is pretty good. Even in the worst conditions, in an aggressive environment, you're assuming 85% of the overall design strength. Now, when we go to glass, we assume from day one, even in the best case scenario, you have 75% of your initial design strength. And in the worst case scenario, you have 50% of initial design strength. So the question becomes, why would anyone ever choose glass? And there's a few answers there. Glass is a little bit more economical than carbon. So depending on the type of the repair, if it's not a large scale repair, it might be just a better option to go with glass. Glass is, it creeps over time, so it's not really good under sustained loads. However, if you are reinforcing a structure for seismic conditions, glass actually might be ideal because it's not a sustained load. The other instance in which you would choose glass over carbon is in, again, a hospital setting where you have, for example, an MRI, because glass is not conductive, whereas carbon is. And so carbon really can't be used in areas where there is magnetic equipment around, because it could potentially disturb that equipment. Another important factor that should be pointed out here is that FRP is to be used as supplemental reinforcement. You can't have FRP being really the only tensile reinforcement you have in a structure. So there's a check built into both ACI 562 and ACI 440, where we see that the existing structure has to be capable of maintaining the load of 1.1 times the dead load plus 0.75 times the live load. And the reason that this is important is because if you look at different materials when they're exposed to fire, we see that steel, when it's exposed to fire, there's a reduction factor put in place. Concrete, the same thing. You have a fire, you have to reduce the material strength. FRP, we assume, just goes to 0. And the reason is the epoxy that's holding FRP in place has a very low tolerance for excessive heat. We usually assume that if epoxy is exposed to temperatures of between around 140 to 180 degrees Fahrenheit, it essentially liquefies and can no longer transfer the load from the structure to the material, whether it's carbon or glass. So we assume no material or no reinforcement there. So that's why it's important to, again, have to make the check that the structure can hold its weight on its own, because you don't want an abrupt collapse or an abrupt failure of a structure. So when you look at the applications of FRP, if you look at this beam, you have a load going over top. We have flexural strengthening, and similar to where you would install steel rebar, you would reinforce for structure for flexure at midspan, and then over top above the columns. For shear strengthening, as opposed to stirrups, you would have a U-shaped cross section of FRP to take the shear load. And in confinement applications with FRP, they act similarly to horizontal reinforcing steel. So going into flexural strengthening, they can actively reinforce for beams, slabs, walls, depending on the conditions of the concrete, the dimensions of the concrete, the strength of the concrete. You can potentially increase the capacity up to 70%. It does not, however, appreciably reduce deflections. I get this question a lot in terms of, can we assume that there's a reduction in deflections? The answer is no. And the why is really that it doesn't decrease, or it doesn't increase your I value. So without that, you really don't get any increase or any reduction in deflection. As I showed earlier, it's easy to reinforce in multiple directions. So here there's a two-way slab, which is easily reinforced in multiple directions. It's easy to reinforce around, for cutouts. So for example, this application here, they needed to extend in an HVAC unit through the slab, and you can see if you're really focused, little circles here where the rebar was cut. So because that rebar was cut in these locations, that's an area that's no longer able to take load that was initially designed to take. So they were able to reinforce using FRP around that cutout. I don't really advocate for the method in which this guy is installing the system, but nonetheless, the design is sound. Using FRP for walls, so here we have a below grade CMU wall where they wanted to reinforce for the soil pressure that's taking place on the opposite side of this wall. So they were able to install FRP systems there. Blast hardening, which I mentioned earlier. This project was for a government building in Washington, D.C. And it was an office building which had a parking garage built right underneath. And the concern was that if for whatever reason there was like a car bomb that went off, they would be able to protect the people in the office building. So they essentially carpeted the floor with an FRP system, which led to what I have here on the slide, moment reversal, where the idea here is that the force in the event of an explosion would be coming from the bottom of the slab, making the top of the slab where you'd have your positive moment occur, and we wanted to reinforce with using FRP. And again, it's easy to conceal. So they were able to easily go in after the fact, after the installation, and then carpet this and then place tile and make it look like a standard office building where you wouldn't even notice the FRP. Getting into kind of some of the theory behind flexural strengthening, I like to show this slide because I think it puts people's minds at ease because, like I said, relatively new in construction, a fairly niche kind of area to focus in. But if you look at the moment equation, where we're calculating the essentially the moment on for the reinforcement, you have the area of the steel times the strength of the FRP, or times the strength of the steel, and so on. And then the FRP equation is essentially exactly the same. The only difference is that that instead of steel, you have a different material characteristic. And the other difference, which actually plays to the benefit of the FRP system, is you have a longer moment arm. So instead of using the depth, which we see here, to the location of the steel, we actually can use the full height of the beam because that's where the FRP is. So you actually do benefit a little bit from the extra 2 inches of moment arm. So not only is the material stronger, it actually based on its location can actually reinforce a bit more. Really the governing factor when we design these types of systems is debonding. So in most cases, we can't actually reach the full strength of the material. So as I mentioned, the strength of carbon is 550 KSI. However, we really can't utilize that full strength because the epoxy bond is really the limiting factor. And that's, you can see here visually using, or with this graph, that we can typically assume to get, in a best case scenario, around 380 KSI due to the debonding factors that are placed. And when you look at the debonding strain represented here by this equation, it's the N term is the number of layers. So as I mentioned, you can layer systems over top of each other. However, it's not a linear progression because with each additional layer, the debonding strain decreases. So so the idea here is that, well, you know, again, 2 layers is not twice as strong as 1, and so on. Again, represented here. So you have an unstrengthened beam, which is represented here by the orange line. Again, it'll take load until it'll yield, and it eventually will reach failure. Whereas FRP will extend that, and you can see the spacing between 1 and 3 is greater than 3 and 5. 5 layers is typically the plateau. We wouldn't do any more than 5, because after that it doesn't really add anything. And you can see here that the dotted lines represent that essentially if there is an FRP failure, the assumption is that the beam should still be able to hold its own or still be able to take the load. It will just slowly start to yield at that point. So getting into a case study for a bridge in Washington State. The bridge was built in the 1960s, and they were looking at over a mile-long span of the bridge, which consisted of 132 spans. And the challenges for this particular bridge was really summed up by extreme concrete deterioration, which was caused by corrosion. The slide says moderately corroded, but I would say a little bit more severe than that, which led to actually a loss of continuity in the steel. So it was so bad that in some areas there was assumed to be no tensile reinforcement. So the first thing that you'd have to do is you can't just start applying FRP. You actually have to repair the substrate. So a concrete repair material with a corrosion inhibitor built in, so that corrosion is not an issue in the near future, was used. Again, more of an application of that. And then they can apply the material. And in this case, each layer of the fabric was less than 1/64th of an inch thick when they were applying it. And so the work was completed in September 2007 in 90 days. So again, over a mile-long span, completed in less than 3 months. And the total construction cost was $10.8 million, which might sound like a lot, but again, the really selling point is the reduction in labor required. So if you were again required to pour more concrete essentially, or add more reinforcing steel, all of that is extremely time consuming. Moving on to shear reinforcement. So here we have the picture details where you would actually bond the strips vertically, just like a stirrup internally. And they can be discrete strips or continuous, so you can actually have the strips go in one lengthy kind of go. In this case, I like to show this slide because it does show that, you know, the similarities between the FRP and typical stirrups. However, this isn't very much reinforcement. It's, I mean, not a very standard application, but I think the visual that helps kind of with the understanding. Similarly, with the flexural application, to strengthen the standard beam in steel, to strengthen a standard beam using steel, the equation is essentially exactly the same. You're just using the FRP characteristics as opposed to steel. There is one caveat, however. You can actually angle the fabric to optimize the reinforcement. So shear occurs at a 45-degree angle. You can angle the fabric to occur at the 45-degree angle to be able to resist the optimum amount of load that it can. In practice, we usually just keep it at the 90 degrees. And to be quite honest, the reason that we do that is because we don't want any mistakes to happen in the field where they don't, quite cut at the 45 degrees. So, if you're in the field, for example, no one's really going to break out a protractor to measure a 45-degree angle and cut the fabric. So it's in most cases, unless we really wanted to optimize the system, we wouldn't stray from the 90 degrees. As with flexure, the main failure mode that we kind of have to be cognizant about is the debonding that can occur with an FRP system. And if you look at the graph for the debonding strain, it's actually a much more severe problem with shear than it is with flexure. So there are some methods that you can do to kind of increase the bonding of shear. You can actually anchor the strips at the top. So for example, if you wanted to place embed the top parts here of the fabric into the concrete and then apply an epoxy over top, you can actually assume a stronger bond. But I would say that's kind of rare and usually in applications where we have trouble meeting the strength requirements specified. So a case study regarding shear. This is the Iowa City wastewater treatment plant, constructed in 2003, so a very new project, and this repair actually took place several years back. So they noticed very quickly in the precast concrete structure, which had a double T roof, severe cracking, and they noticed that they have pretty much a textbook shear crack going at the 45-degree angle, but they also noticed the splitting crack towards the bottom of the double T. And so they actually brought in a third-party engineering company to do a little bit of forensics to see what was going on. And what they found was this: the as-designed condition had a shear or a steel web to take the shear load, and then they had an L-shaped hanger bar that was designed, that was included in the design as well. And what they found was this: the as-built condition for that the precaster constructed with these beams was that the reinforcement was missing right in the location where shear is most prevalent, and the bar was not centered. It was moved to slightly to the right, so that when you have load acting on top of the beam, it actually pushes the hanger bar to the side a little bit, resulting in the cracks that we saw in the photos. So this project had severe to moderate cracking in 48 double Ts. 196 total stems were affected. So they actually looked at a number of repair scenarios to decide ultimately what they wanted to do. The first is actually my personal favorite. They called it virtual strengthening. So basically, every time it snowed, they would send someone up to remove the snow from the roof, and that way they can assume there is no snow load, and that way they wouldn't have to do anything. The other thing that was considered was a structural steel retrofit, so bonding steel saddles, basically in the U shape, to the outside of beam. They thought about replacing the roof in its entirety, so replacing the double T sections, and then finally they considered installing FRP systems. And being that this case study is in my presentation, it's a safe bet to assume that they went with the FRP. So they applied a system that was able to resist approximately 30 kips in shear using one layer in a continuous strip from one end of the shear location to the other. As I mentioned, in shear applications, the fibers have to be oriented vertically. And we see here one layer of the layer epoxy going on, and then finally the fabric, and then another layer of epoxy will go on after that. And then finally, it was coated with an acrylic coating that is resistant again to UV and again for aesthetic purposes, so that really you wouldn't even know if you weren't looking for it that FRP was installed. Finally, getting into column wrapping or confinement. There are a number of reasons why you would want to confine a column. The first shown here is to reinforce in seismic. So this earthquake took place in Kobe, Japan, where you can see, I mean, very clearly the method of failure was torsion. The beam is kind of twisted around itself. And had they installed steel ties at the top of the beam, they wouldn't have had as severe an issue. However, you know, hindsight's 2020. So there are a lot of these structures that are currently in existence that aren't reinforced as they should be. So you can install FRP. So existing concrete columns shown here. This is actually an Amazon facility where you can see, again, it doesn't really take much cross section. And I believe, if I'm recalling correctly, that these were actually designed to resist seismic loads in this particular facility, because this facility is in Seattle, Washington, which is kind of along the fault line there. So again, it doesn't take any additional space and can be reinforced relatively easily simply by wrapping the column. Now, if you look at confinement, and I won't really, as opposed to flexure and shear, I won't get really into the calculations because the calculations for confinement get very complicated very quickly. But if you have an unconfined column and you apply a load to it, in excess to what that column was designed for, the concrete cracks. And if you have that same column and you reinforce it with FRP in a horizontal orientation, the concrete still cracks, but it's being held together by the FRP around it. And I liken it to just a simple example of, if you have a cylinder of sand and you push down on it with your finger, it wouldn't take very much effort for you to completely destroy that cylinder. But if you take that same cylinder of sand and put it in a can of Pepsi, and then you push down on it, it can actually resist quite a bit of load only because it's being confined. And that's really what's going on here. So with a few layers of this material, you can take 4,000 PSI concrete and actually make it look like 7,000 PSI concrete. And one quick note before I move on is, as opposed to flexure and shear, we don't really concern ourselves with the debonding failure. Because confinement is what we call a contact critical application, not a bond critical application. So again, because the material essentially bonds to itself, you can do in theory an unlimited number of layers of this material, and it wouldn't decrease the efficiency of each subsequent layer. Just one thing to keep in mind. Getting into the installation requirements for installing FRP systems. As I mentioned, you have to actually go through and conduct a concrete repair, so removing any unsound concrete, repairing any corrosion damage, and then the references for doing this are shown here. ICRI, which is the International Concrete Repair Institute, has lengthy documents concerning this. Surface preparation. So you want to open the concrete pore structure for a number of reasons. One, the bond with the epoxy is a chemical bond, but if you can open the pore structure to where the epoxy can slip through, you get also kind of a mechanical bond. The other thing is the very first layer of concrete, the first few millimeters, is the weakest layer. So if you can remove that, you'll ultimately get a much stronger bond between the material, the FRP material, and the concrete substrate. Again, there is an ICRI standard for how to do this and what that substrate should look like. If you have any cracks that are greater than 0.01 inches, then they need to be injected with epoxy injection resin. And the reason is that if you don't, there is the potential for buckling in the FRP material. So here you see they coated over it, but you can see where the material buckled because they didn't inject a crack. So that area was an area that was not taking load, and then it buckled the FRP material. There are some constraints in applying the material or the conditions for applying the material. So you can't apply in temperatures that are below 40 degrees because the epoxy won't cure. So you would have to either heat the area or wait until wait for warmer weather. And then the material or the substrate can't be filled with water or moist because it will result in this. You'll essentially entrap the moisture inside a column here. So here they completely wrapped a column without giving any space for the water to escape, and they did this actually this application in the morning, and then because the sun started beating down on this column, it extracted the moisture to the surface, resulting in these bubbles. So in hotter climates where moisture is an issue, we recommend actually doing these applications at night, because during the day, most of the moisture will already be expelled from the substrate, and it will result in a cleaner bond where you won't have this issue. Getting into a few QC tests. The simplest one is just a tap test. So you can go around and tap the FRP material to search for any hollow locations. So if it sounds solid, you have a good bond. If it sounds hollow, that's an area that's not bonded. The next is a pull-off test where you bond a puck or like a steel kind of shape here to the concrete or to the substrate with the FRP, and then you use an alcometer to do a pull-off test. So on the right, we see what would you consider a failing test, because the failure resulted between the epoxy and the concrete. So that the bond isn't strong enough. On the left, we have a passing test because the bond was strong enough to actually break the concrete, as opposed to the layer of or the layer connecting the epoxy with the rest of the system, with the substrate. And finally, the last QC test I'll talk about is a witness panel. Witness panels are essentially squares of FRP materials that are brought into a testing facility after they are made and then tested for tension. I am not a big advocate of witness panels, because really it only tests the material. You're only seeing how strong the material is in tension, and you're really testing how well can you make a witness panel. It has nothing to do with the actual installation of the system. They're still mentioned in detail in ACI, but typically we would advise against them. It's better to actually test the installation of the system. And then finally, getting into where, as a manufacturer, master builders kind of comes into play. We design these systems after an engineer specifies really the conditions that need to be addressed. So if a beam is deficient X and Y in shear and flexure, we would design a system to compensate for those deficiencies. Similarly, we would provide designs so that when it goes to the field, the contractor can install the material in the proper location and using the proper using the number of layers that are specified. And then offering field support if necessary, if it's deemed that the project it's crucial for the project. And finally, we do at times kind of the hands-on trainings for installing these materials. So this is a very old picture before my time, but this is actually our R&D facility in Cleveland for master builders. And that concludes my presentation. So if anyone has any questions, feel free.
Thank you so much, Hazem. If anyone has any question.
Actually, I do. Until now, it seems like, can you hear me?
Yes.
Yeah, until now, it seems like FRP applications have been exclusively kept for rehabilitation purposes. And, do you think that other than sort of the rebar, the FRP rebar, do you see, FRP panels or plates being used in the future for structural purposes?
You mean in new construction?
Yes.
I guess no, really the short answer is no, because the panels like the laminates or the fabric materials are, like, as I mentioned, much more costly than steel. And you really wouldn't get a time benefit like you would in rehabilitation with new construction, because it's easy to just place the steel rebar and then pour the concrete after the fact. So there really wouldn't be a time savings, and the material cost is much higher. So no, not with those. The only thing I can speak to is that as far as rebar is concerned, they do currently we don't, but there are currently manufacturers that produce glass GFRP rebar that you can use in place of steel rebar. It actually has much higher tensile strength, and again, it doesn't corrode. But it hasn't been very widely adopted. But in terms of using the panels, no, I don't see that happening, just because you wouldn't really save any time, and it would cost just a lot more money.
I see. Thanks.
I have one more question. So, like you said, that it is pretty expensive to have these systems, and that the primary mode of failure is not the material itself, but the debonding after epoxy. So, let's say once a structure has been reinforced with this and it debonded, the material itself, the expensive material itself, has not degraded a lot. So it is still capable. So is there any application after, or reusing or recycling debonded FRP thing?
Yeah, that's an interesting question. I would have to say also no for that one, simply because then you're dealing with a compromised material in terms of the surface of it. So if it failed the bond test the first time, you really wouldn't want to risk it the second time. You would want to get a new material to where it can have a stronger, again, kind of more of a mechanical and chemical bond to the substrate, as opposed to material that you'd have to go through the trouble of cleaning it to remove any concrete residue and all that kind of stuff. It just I don't think the risks would outweigh the potential cost savings.
Yep. Go ahead.
I have one more question. Are there any alternatives to epoxy for bonding FRP with the concrete?
Alternative epoxies. It's interesting that you mentioned that. Actually, someone I work with is currently doing research on not an epoxy, but if you're familiar with methyl methacrylates, which are much stronger. But I mean, essentially they chemically weld to substrates and to each other to increase kind of the bond potential of FRP or fabrics to substrates. However, this type of research has been done in the past. Like I said, we're currently doing this research, but in terms of mainstream industry adoption, it pretty much is just standard epoxy. I mean, the only thing that's mentioned in ACI 440 is an epoxy, and as I mentioned, I think they cite the debonding or the failure point of an epoxy at a certain temperature. which is between 140, 180 degrees Fahrenheit. So so currently nothing really in terms of wide industry adoption other than epoxy, but you know, you never know. Like I said, FRP has been around for 35, 40 years. It's kind of just starting to pick up a little bit of steam. So there's ongoing research in terms of different alternatives, but I don't think in the near future we'll have anything.
Thank you.
Anything else?
I think that's all we have. Thank you so much for the interesting presentation, Dr. Jadallah.
Perfect. Thank you.
Really appreciate it.
Thank you, guys. Thank you for having me. And good luck with your elections for whoever's running. And if you guys ever, I probably should have put it on the slide, but if you ever need anything, you know, to anyone attending the presentation, Ahmad has my contact information. Please feel free to reach out, and we can have a discussion.
Sounds good. Thank you so much.
Thank you very much.